Okay, so let's start. We were discussing in the last class, I was trying to give you a motivation as to how to go about making a kind of a mechanical amplifier. And the reason for choosing that course of action was to see if we can draw an analogy between something which we know intuitively to something, if we can connect the same principles to an electronic amplifier, right? So a quick recap. So what were we saying? Let's say we have a reservoir of water or some liquid, and you have a fat pipe that comes in, and maybe there is a piston here which can go up, which can move horizontally, and you have water, and I mean, the spring is connected in any way you want, right? So let's say this spring is connected like this. And depending upon how much water flow you have, this guy can move up and down. And the water flow essentially is being controlled by somebody who is moving this piston horizontally. So now if I mean, as we intuitively understand that this piston can move at max, in and out at max. The range is the diameter of the pipe. So, so for, let's say, I mean, if this is 1 centimeter wide, if for 1 centimeter movement of this piston, you can, depending upon how thick the pipe is, what is the flow of water, how long the pipe is, based on that, you can have modulation of the flow of water here, which essentially means that, again, I mean, this platform can move up and down depending upon where the piston is at any point of time. So clearly, you can see that you can design this entire thing in such a way that this delta x and this delta y are not same, right? So you can always design the system in such a way that delta y can be much more than delta x, which means you have gain. In this case, the gain is in terms of the distance covered. Also, you might want to see whether one might argue that whoever is in charge of implementing the delta x is also spending some power, and depending upon the size of the platform and the weight of the platform, delta y, when you calculate delta y, that also will correspond to some work being done. So that ratio also can be more than 1, right? So which means you are essentially having kind of power gain. But where from is the power gain coming? Where from the extra energy is coming? The extra energy is coming from the water that is stored. Essentially, the potential energy is getting converted to some sort of kinetic energy, but it is being controlled through a third terminal, right? So the control is the most important thing, right? So as you will see in design, any sort of design, mechanical, electrical, or any sort, you would like to have control. You would like to have a control over whatever you are trying to change, right? Without any uncontrollable phenomena is almost unusable, right? So in design, we like to control whatever we can. So this principle we were trying to also see if we can use this principle in our electronic systems. And the analogy that we are again giving was that I mean, what is a reservoir equivalent in an electronic system? It's a voltage source. So let's say we have a voltage source. What is I mean, this pipe is essentially a medium through which water flows. So in an electronic equivalent, let's say have a piece of metal or a piece of conductor through which the carriers flow. So now, how are we modulating the water in the mechanical analogy? We are trying to deplete the amount of water in this region where the piston has a control, right? So similarly, the similar thing will be, let's say we identify a region here where we have carriers. We would like to deplete that, right? Using a third terminal. Now, when you have electronics charges, right? We have movable electronic charges. The only handle that we have, one of the handles that we have, I shouldn't say only, one of the handles that we have in an electronic system is the use of a capacitance, right? If you use capacitor, then it's possible to influence the amount of charge in one of the plates. But in that case, the capacitor has to be transverse, right? So it has to be, so if you add a separate voltage source here, so then this electrical lines of forces can change the charges here. Now, depending upon how much voltage difference you have accrued, the amount of charge that will accrue on the capacitor plate can also change. But there is a critical difference between this configuration and the configuration on the left, is that even though you will probably be able to influence the charge here, you will not be able to influence this current, because in a conductor, essentially you have infinite supply of charges, right? So essentially, the current will always be dependent upon this vertical electric field and not on the transverse electric field if you are using a conductor. So that's one critical difference. So which means because we have this difference, we essentially then say that these type of, if you take a piece of metal, a piece of copper, or a piece of aluminum, you will not be able to use this, even though it looks like similar principle should apply, you will not be able to use. Okay, but as it turns out, there are classes of metals, there are pieces of semiconductor which you can use to get this exact same phenomenon. So that's what we will study in the rest of this lecture. Okay. Again, this will be very anecdotal, very intuitive, basically no maths involved. The only that part that I'll get to focus on is that part that will be necessary in order to move ahead with the circuit design. Okay, so if you want a very detailed version of how these devices will work, I'll encourage you to take up the course 311. That's essentially a full course on how a device works. Okay. Okay. So now let's go back to whatever we know about semiconductors. So here I'll be banking on your existing knowledge on how a hole works, how an electron works in a piece of semiconductor. So quick recap is, let's say we have a piece of semiconductor, which is, it's a piece of silicon. It's a piece of undoped silicon at 0 Kelvin. Right? So outer orbital has 4. So you have Si and you have, so these are all covalent bonds. So at 0 Kelvin, where there are no thermal fluctuations, we know that all so let me ask you this. So at 0 Kelvin, do you think there will be any free electrons? No, right? So all the bonds are perfectly satisfied. Right? There are no free electrons. Now let's say I increase the temperature, I bring it to room. Some of the bonds are going to break. Some of the bonds are going to break. We don't know which are going to break because it's a statistical phenomena, but we know some of them are going to break. Now, when they break, what's going to happen? You will have free electrons and free holes moving around. All over the piece of semiconductor. Now, if we apply, let's say, an electric field or a battery between these two terminals, what is going to happen is, now since we have mobile charges, right? We have electrons and holes which are moving at all points of, everywhere in the piece of silicon, we are going to see a flow of charges, right? We are going to see a flow of charges. The electrons will get attracted in this direction. Electrons will get attracted in this direction, and the holes will get attracted in this direction, and the holes will get attracted in this direction, and the electrons will get attracted in this direction, and the holes will get attracted in this direction, and the holes will get attracted in this direction, and the holes will get attracted in this direction, and the holes will get attracted in this direction, and the holes will get attracted in this direction, and the holes will get attracted in this direction, and the holes will get attracted in this direction, and the holes will get attracted in this direction, and the holes will get attracted in this direction, and the holes will get attracted in this direction, and the holes will get attracted in this direction, and the holes will get attracted in this direction, and the holes will get attracted in this direction, and the holes will get attracted in this direction, and the holes will get attracted in this direction, and the holes will get attracted in this direction, and the holes will get attracted in this direction, and the holes will get attracted in this direction, and the holes will get attracted in this direction, and the holes will get attracted in this direction, and the holes will get attracted in this direction, and the holes will get attracted in this direc attracted in this direction, right? So this is the electron, this will be the holes. And because we have both electron and holes, which are essentially now contributing to current flow, right? Both electrons and holes are essentially contributing to current flow. You are going to have some current, but their contribution will be equal. Since the density of the electrons and the holes are equal, right? So we'll be getting twice the amount of current, right? That we would have gotten if we had only observed the electrons. Okay, so again, a very important difference between how a metal works and a semiconductor works. In a metal, you have only one type of carriers. In a semiconductor, you have both. Simply because the way the carriers have been generated. In this case, the carriers have been generated by breaking covalent bonds. The moment you break a covalent bond, you create a electron-hole pair. And when you apply a electric field, both of them move. Now, again, sometimes it becomes difficult to intuit why a hole moves. So hole is ultimately a vacancy. But if we peel down one more layer, we understand that whenever we move, whenever we apply an electric field, maybe there is a neighboring bond neighboring bond to a hole which breaks, and that electron from that bond fills up this hole, which essentially means that a vacancy has moved. Right, under the influence of electric field, since the vacancy is moving, we call that even the vacancy has moved, even though due to the movement of an electron from a neighboring fulfilled bond to a vacant bond, we understand that essentially means that we can model that as a whole movement instead of thinking that every time a new bond breaks, right, and fills up a hole, we can simply say the hole moves. So that's essentially a hack that people use to ensure that we simplify the mathematics. Essentially, it's easy to identify, it's easy to track one vacancy than track millions of breaking of bonds, right? Okay, so, okay, fine, this is all good. But then, as it turns out, this is also not super useful in our case. Okay, it's Ni. Okay, since it will not be useful, let's forget about it. So, the another stuff that is generally done is to say that, okay, this is the intrinsic piece of pure silicon. That's all good. But then if we take this same piece of pure silicon and we dope it with an impurity, and not any kind of impurity, well, let's say an impurity which has 5 electrons in its outer orbit, right? For example, arsenic or phosphorus or something. Then we basically dump those atoms or those atoms into this piece of silicon. So what's going to happen? Some of them are going to replace some of these some of these silicon atoms, right? I mean, not all, but some of them are going to replace a silicon atom. So essentially, so here it was initially silicon. Now let's say it becomes arsenic. Okay, and let's assume further that the neighborhood is all silicon, right? This argument only works when you have. It's not as if most of the silicon atoms got replaced. Only some of them got replaced. So if that is the case, then if we only observe that arsenic atom which got embedded, which replaced one of the silicon atoms and stole the lattice. So in that case, we're going to have one extra electron which is floating around, because that's the unfulfilled bond. And as it turns out, again, I mean, not a part of this course, as it turns out, the amount of energy that is required to generate an electron-hole pair in case of a pure silicon, and the amount of energy that you require in order to free this extra electron in a arsenic doped silicon is quite different. In case of a pure silicon, the amount of energy you require is approximately 1.1 electron volt. Again, electron volt means it's basically charge of electron equivalent to that converted into energy, right? So So as it turns out, in the case, if you dope it with an arsenic, that extra electron you can get at almost a tenth of the, by spending almost a tenth of the power, or 10% of the power with respect to what you have gotten in case of a pure silicon. So for all practical purposes, you can assume that if you dope your silicon with, let's say, arsenic, then almost all the arsenic atoms will contribute an extra electron, because at room temperature, almost all of them will be able to will lose that extra electron. So if you dope this arsenic atom with, let's say, a concentration of say we call this ND. D means donor because it's donating an electron. So if the concentration is ND, and let's assume we have doped in such a way that ND is much, much greater than Ni, right? So Ni is the number of, and again, Ni is the number of mobile electron and holes, right? So Ni is equal to concentration of mobile electrons. Note, this is not the concentration of the, we are not saying Ni is the concentration of the number of atoms in a lattice. Okay, number of atoms in a lattice for silicon can be much higher than Ni, because not all of the atoms is going to contribute to an electron. Okay, so but in the case of an arsenic atom getting, in case of the, in the cases where we are doping the silicon with an impurity, almost all of the arsenic atoms are going to contribute to an electron, because the amount of energy required for the arsenic atom to release an electron is almost negligible with respect to a pure silicon. So if Nd is much greater than Ni, what can you contribute about the type of carriers that you are going to see in this second structure? It will be mostly electron dominated, right? It's still going to have some holes, right? It's still going to have some holes. But if you see across, it will be mostly electron dominated. Okay, so this type of doping is called, when we dope and semiconductor with large amount of donor atoms, right? Donor atoms. What we essentially say that we have this is an N-type doping, right? This is an N-type silicon, so this becomes an N-type silicon. Okay, the N means essentially we have doped it with the type of impurity that is giving us negative charge, that is giving us electrons. So now, can you now? Yes. It's the concept. Ideally, it should be the concentration of arsenic, but the approximation is they are almost the same, right? They are almost because almost all of them. It's very easy for an arsenic atom sitting inside a silicon lattice to lose an electron. So essentially, they are almost the same. So now, one more important key piece of information is, so this electron that gets contributed to the lattice is now free to move, right? Because it's not as if it's a part of that arsenic atom anymore, because it doesn't have enough. It has essentially lost it to the lattice. You give a electric field, the electron can move away from the neighborhood of the original mother atom. Okay, so essentially, if this electron moves away, what can you say about? Okay, let me ask you this now. When we say that the number of essentially the electron concentration here is much more than the hole concentration, right? So here in this case, obviously the electron concentration will become much more than hole concentration. But in the case of on the piece of silicon on the left-hand side, clearly the electron concentration is exactly equal to the hole concentration. Correct? So does that mean the dope lattice is ionized? It's not electrically neutral? Yeah, why not? Correct, right? So essentially, whenever an arsenic atom loses its electrons, it becomes positively charged. Excellent. So this becomes positively charged. So this becomes positively charged. But this positive charged ion is not mobile. right? This is the critical difference, that you are still going to have localized positive charges, but it's not going to move under the influence of electric field. Okay. So so now if this is the case and you apply a battery, here, for all practical purposes, I can say that it is only the electrons that are contributing to the flow of charge, right? Granted, there are still some holes, right? But the concentration of holes will be much smaller. It will be orders of magnitude smaller. Typically, these dopings, this ND, the ratio of ND over Ni goes of the order of 10 power 8, 10 power 5, 10 power 6. That is the order of doping that we do. So essentially, you can say that the concentration of electrons is much, much, much higher than concentration of holes. So for all practical purposes, we can neglect the contribution of holes to carrier transport. Okay, in a doped silicon. Okay, fine. So now why is this helpful in our case? It is helpful in our case because now see what's going to happen. Now let's say I take this piece of silicon and use it in the same method that we were trying to use. So let's say I take this piece of N-type silicon. Initially, let's say I don't apply any voltage. Let's say these two are shorted. Okay. So I put another metal plate close to it. And let's say I give a negative charge to this plate, right? You will soon understand why I'm giving negative charge or negative voltage in the way I have connected. So what's going to happen? An electric field is going to form, and the electric field will go in this direction, right? Now let's further assume this is metal. So can you comment on the type of charge that is going to accrue here? It's going to be positive charge, right? Okay, but this is an N-type silicon. Where from are you going to get the positive charge? Right. So essentially, so again, very good. So essentially, what's going to happen? You have in this N-type silicon, you have these fixed charges which are not moving, and you have mobile charges, electrons, which are moving around. Now, if you apply the electric field in the direction that I have shown, what's going to happen? The electrons, it's not as if the positive charges will rush to the surface or to the edge. It's just that the electrons will move away, right? So electrons are going to move away. And whatever will left uncovered will be the positive ionized impurity. So you are going to get, I'm using the right color. I think so. Okay. You are going to get these ionized impurities which are getting uncovered, and the electrons have moved away. Okay. So when the by the way, ionized impurities are present everywhere. It's not as if it's only there. But the key thing is here it is becoming uncovered. You don't have, if you only observe that small region just at the edge, you are going to see it's primarily being dominated by the positive ionized charges. So that small part will not be electrically neutral. Rest of the silicon will be approximately electrically neutral because it's almost equal number of positive and the negative charges. But around this part, around the edge where the electric fields are getting generated or terminated, you are going to see a charged part. Okay. So now, if let's say we concentrate, I don't know how, but let's say we design our silicon in such a way that electrons all the electrons can only flow in this small part and not in the rest of the semiconductor. Big if, I haven't said how. If we can do that, then it is arguable that it looks like under the influence of an electric field, transverse electric field or the lateral electric field, I am able to get a piece of silicon where you sometimes have a mobile charge and sometimes you don't. Sometimes you have only fixed immobile charge and sometimes you are going to have some mobile charges. Right? Does that make sense? So if that is the case, which means I have a controlling handle now. It's equivalent to, you can think of this electric field as the piston. Depending upon what type of battery or what type of voltage I am applying, I can make the place completely devoid of any mobile charge, or I can make it filled with mobile charge. So now if then I apply a electric field that goes from top to bottom, then there can be some flow of charges, just like we had in case of water, right? So that's essentially the overall principle, overall thought process rather. Okay, so let's see how we can go about doing this. Yes. Yeah, exactly. Very good question. His question is, if in place of a semiconductor, if we had a metal, won't it behave in the same way? The reason it will not behave in the same way is that you will almost never be able to get the metal devoid of mobile charges. Yeah, exactly, right? So essentially, you will be attracting positive or negative charges to the plates, but it's not as if you will be able to making the place devoid of charges. Everything is mobile in case of metal. In case of semiconductor, there are two, in the low semiconductor, there are two types of charges, but two types of charges don't have similar mobile properties. One guy is mobile, other one is, right? That's why you are able to influence this, right? It's not as if the charge is going off. It's the type of charges that is helping in terminating the electric field is changing. Okay. So now let's get back to this. So now it sometimes becomes difficult to look at everything like this, right? Electric field going from left to right. It's better to look at in a vertical direction. And so let me sketch it in such a way that this entire thing is horizontally flipped, right? Or 90-degree flipped. So let's say you have this bar, which is N-type doped. And you have this piece of metal here. So now if we apply an electric field sufficient, putting any voltage will not work. Let's say some critical voltage, that gives us some critical electric field, which helps in uncovering this region just under the surface. So what's going to happen? We are going to have electric fields which are going to get terminated here. By the way, are we going to have electric field somewhere here? Nothing visible, right? It's almost like a metal because you have sufficient amount of charges, mobile charges there. The rest of the silicon behaves almost like a metal, just that around the surface, you don't have any mobile charges. So the visible electric field will be in the insulated part or in the dielectric part. But in this case, the way I have shown the dielectric is air, but you get the idea, right? So you are going to get electric fields, visible electric fields around this part. Okay. So now another piece of information that we need to be aware of is, as it turns out, in semiconductor physics or in semiconductor technology, you cannot ever connect contacts anywhere you want, right? So let me rephrase. So if we have to, just like the example that we gave here, so if we have to get charges to flow from top to bottom, we have to have a way of connecting a battery somewhere here, correct? Which essentially means that in this case, what we are saying, we need a battery somewhere here. The leads of the battery should be here. But as it turns out, in semiconductor technology, everything is done on a piece of wafer, right? So essentially, you have a uh, piece of silicon wafer. It's almost like a biscuit, a top of a biscuit, big top of, I mean, almost like a 12-inch wafer. The radius of the wafer is approximately 12-inch. That's the standard one that people use. So you have to grow everything on top of the wafer. So if you look from the top, it's essentially a flat surface. So think of it like building a city on top of ground. So you cannot, you dig, you build something, you make flyovers, everything you can do, but it's not as if you can go to the surface and connect something to the sides and connect something like this. Okay. So semiconductor technology is also like this. Whatever you have to do on the surface. So essentially everything here are accessible, but you cannot connect a battery here. Okay. So essentially then we become limited by the understanding that we want flow of charges in just there because that's where our control is, but we cannot connect a battery here. So we have to connect a battery somewhere close by, which means we have to connect the battery somewhere over here. Okay, so you are okay with this guy flow from top to bottom? Okay, so essentially I rotated the figure by 90 degrees, right? So essentially we are trying to the same figure drawn a different way. Question? Yes.
First of all, two questions. Like, how are we going to control that the पूरा एक box था वो,
right?
उसमें आपने just you just separated the electrons to one side.
Right.
How are you going to control कि सिर्फ इधर से current flow करे?
Okay. I haven't talked about it yet. I'll talk about it. Yes.
The second thing is some वाली चीज जो आपने बोली थी कि battery कहाँ connect कर सकता है नहीं कर सकता.
Right.
Could you just please explain?
Yeah, sure. So his question, we have two questions. One, how can we control that the charges flow only in that small part that I have shown and not the rest of the channel, rest of the piece of semiconductor? I haven't talked about it. I will do that later. And his second question was why am I saying that we cannot connect a battery here? So the second question, let me answer first. So as it turns out, so this goes into the technology, how devices are made nowadays. So if I look from the top, right? So let's say I take a piece of silicon wafer. Think of it like a biscuit. You are looking from the top. Okay. So what are you going to see? You are going to see a big. You're going to see a big circle. Okay. And as it turns out, this, let's say, is a 22-inch dia. Okay. So as it turns out, you build, typically, I'm sure you have seen ICs, right? Those, if you open up a motherboard, you see the small black thing, like almost like a spider sitting inside. So that's also not an IC, that's a packaged IC. If you uncover that black thing, you are going to see something inside, which is probably 1/100th of the dimension. That's an IC. Okay, so that you can see that you can understand that the dimension of an IC is not like in inches. So as it turns out, in a particular silicon wafer of let's say 22-inch, you can probably make 1,000,000 ICs. Okay, simply if you scale the sizes that I just talked about, you are going to see 1,000,000. You can get a number which is very high. And that is used because essentially what we do, this piece of silicon is a piece of land almost. You split the piece of land into multiple pieces, and let's say each of these is an IC. So you carve out that each square, and then say that okay, this is your product, and then you package it and put it in a PCB, and then you make a full system. So now, why people do it like this? It's because now you can readily imagine, instead of making one single piece of IC every time, you probably will be able to use one single wafer to make 1,000,000 ICs at one shot. Okay, so again, I'm hand waving many of the important details which are part of technology course, but take it from me, the fact that it is much easier to build 1,000,000 ICs together than one IC separately. Okay, so if that is the case, Now, let's say all of these ICs are identical ICs. Let's say you want 1,000,000 parts, you book a wafer, you develop develop 1,000,000 ICs. But now the question naturally becomes, how are you going to connect a battery in the middle of this wafer at the side of an IC? You'll not be able to. Now, your natural comeback should be, I am not going to use 1,000,000 IC at a time. I'll carve it out, put it out, take it out, put it somewhere else in a PCB, then I can apply. Yes, you can apply. But the issue is, each IC is not one single device. Each IC will probably have 1,000,000 devices of their own. Right? Each of them has 1,000,000 transistors. So which means that if I zoom into this entire thing, right? If I zoom into this entire thing, so this is a big piece of square which has, 1,000,000 transistors inside. So I'm drawing the transistors as squares, somehow interconnected. But let's say you have a transistor somewhere over here, you don't have access to its sides. You don't have access, you cannot have, it's almost like saying that on a sheet of paper, you have made some drawings. How are you going to connect, let's say, a piece of house that you have drawn on a piece of paper and connect something to lateral dimensions? You'll not be able to. You have to go vertically. So essentially, the leads go from top. The leads go from top. Okay, so that's a practical problem. That's why here what I am trying to show is in case of one device, but you have like 1,000,000 of them in a piece of semiconductor. So you cannot have lateral connections for 1,000,000 of them, but you can probably have a vertical connection because from top you can access each other.
Okay, those two small batteries or sort of thing are connected like this.
Yes. Okay. Yes. Okay. Okay. Very relevant questions. Okay, so now, so if I have to connect a battery, I probably will now connect a battery like this. This battery is obviously not connected underneath the wafer on top of the wafer, but you get the idea. Okay. So now if you have this, now the question is, so before I come to the question, this is a quick reminder. This is an N-type silicon. So you have electrons, mobile electrons, mostly everywhere. You have applied an vertical electric field in this case, which has successfully driven away the electrons from the surface. And we have only the immobile positive charges just underneath where I have shown. So now let's come to that question of how do we ensure that we have only, the flow of electron is only limited in the channel that I want and not anywhere else. The way we ensure that is as follows. So if we say that in this piece of silicon, the primary carrier transport is due to electrons, right? So then I apply, let's say I carve out a place here and say that. So again, another important piece of information is that it's not as if you simply take that, I'll connect the metal on top, it's going to work. You have to dope that area with either an N-type impurity or a P-type impurity. I haven't talked about a P-type impurity as of now. So essentially, so an N-type impurity is something which has 5 electrons in its outer shell, and P-type will be which has 3 electrons in its outer shell, which essentially means that you get a hole out of it, right? So I assume you know this. You know this, yeah. For example, boron is a P-type impurity. If you dope, similar to an arsenic that the example that I took, if you dope a piece of silicon with boron, you are going to get overwhelming majority of holes. And if you dope it with arsenic, you are going to get overwhelming majority of electrons. Okay, so now we have 2 options. When we are connecting these metal leads, we can connect it in such a way that there are here I have mostly, an N-type doping, right? You have mostly an N-type doping. So let's assume this is N-type doping. and I connect the battery like the way I have shown here. So in this case, do you think there will be flow of charge between the leads of the batteries? So here you have electrons because that is n-type dope, right? The silicon is also n-type dope. So everywhere you have a lot of electrons, right? So now I connect the battery the way I have shown. So do you think there will be flow of current? There will be, naturally, right? It's almost like a piece of metal where I have connected two leads of the battery. Is there any way I'll be able to stop this current from flowing? Yeah, it looks like I can do that by increasing this vertical electric field so that this the entire piece of this vertical dimension gets filled with only positive charges, right? But that is not a very trivial thing to do because these wafers are not that thin, right? So amount of voltage that you will require will be quite high, and that is another thing that comes into picture why you cannot do this. I'll talk about this hopefully in another 2-3 minutes. So take it from me that it's not very trivial to do this. That is, you keep on increasing the voltage and you get the entire piece of silicon devoid of any electrons. So if that is the case, then looks like we'll not be able to control this electron flow like we desire. But we have another type of doping to explore. So let's explore that. So let's say this guy is p-type doped, which means you have, this is p-type doped, which means you have primarily holes here. In this small section that I have sketched. Not everywhere, only in the small section. Okay. And I ensure that, so this is a PN junction now, right? So this is P, this is N. Vertically, that see, it's a PN junction. Right? It's a p-type of silicon and an n-type of silicon connected next to each other. It's a PN junction. Now, what do you know about a PN junction? If a PN junction is forward biased, it is going to push in a lot of current. It's going to allow a lot of current. If it's reverse biased, it's not going to allow any current. Right? So let's further assume, make an assumption that the battery voltages have been adjusted in such a way that this PN junction is reverse biased. Okay, again, that is in our control because we can control the battery voltages, right? So let's assume this PN junctions are reverse bias. So okay, so if we do that, then under any circumstances, do you think an electron or a hole can flow in this direction? No, right? Reverse bias change junction, nothing can flow in principle. There is still some leakage, but let's ignore the leakage for the time being, right? So no electrons can flow. So what are we doing? We are essentially saying that whatever come what may, whatever happens, this flow is not allowed, right? So essentially equivalent to this analogy, what we are essentially saying is this flowing through the body is not allowed. We haven't yet said what can happen in that channel, but at least we are saying that flowing of charges through the body is not allowed. So if that is not allowed, let's now concentrate what might happen in the channel or channel. Yes. Okay, so let me take a step back. So let's say this guy was an N-type doping. So this was primarily filled with electrons, right? Mobile charges by electrons. The piece of silicon is also N-type dope. So that is also filled with primarily electrons. So it's almost like a piece of semiconductor, which is only doped with electrons. Now I apply this electric field like the way I have shown here. So naturally, electrons are going to flow. There is no way you can control it, right? Because you might be able to control this region by making it devoid of any electrons, but there is whole entire substrate or wafer which is there to provide the extra electrons. So what we then say is that forget about this N. So let's dope it with a p-type impurity, maybe boron. So now something interesting happens, that this becomes a PN junction, right? So essentially, this is a PN junction. Correct? So by ensuring that, by putting in a bias in such a way that this PN junction is reverse biased, all we are doing is we are saying that this path is not allowed anymore. Right? So if a carrier has to flow, it has to flow through that space that is just underneath the capacitor. It cannot flow through anywhere else. Okay, fine. So far so good. But the real question remains, this guy is still devoid of any mobile charge, right? The carrier, the place from which I want carrier transfer to happen doesn't yet have any mobile charge. So still we will not be able to get any current. But now let's see what happens if we keep increasing this electric field, this vertical electric field. So let's say I keep increasing this electric field. So basically what I'm saying is that I am cranking up the battery voltage, right? So it's the reverse way I have connected. So if I say that it's connected like this. So if I keep increasing, sorry, I didn't draw it the right way. So I am bothered with this battery, right? The vertical battery, this battery. So if I keep increasing this battery voltage, so this electric field, the vertical electric fields, right? The electric fields here are going to increase. So what's going to happen in that, just in the semiconductor which is close to the surface? Arguably that you will be seeing more and more electrons which will be rushing away from that surface, and you'll be uncovering more and more immobile charges, right? So you'll be essentially saying maybe the amount of immobile charge that was there earlier which was just around the surface. Now it will be now if you go slightly beneath the surface also, you are going to see immobile charges. That's going to happen, but something more interesting happens. What essentially happens is that we till now we have essentially neglected any minority carriers. When I say minority carriers, essentially what I mean is, remember when I said here in this case, even though this guy is doped with N-type impurity, we still have holes. They are much lesser in number, but they are still present. Now what's going to happen is, here by doing all this nonsense, what we have essentially done is made that place devoid of any majority carrier, right? When you have only plus charges, plus immobile charges, we are essentially saying that initially you might have a majority of electrons, but you don't have it now because the electrons have been driven away, right? So we are again at fair playground in terms of concentration of electrons and holes. Now, I'm sure you know this, moment you have all these things is not happening at 0 Kelvin. Everything is happening at room temperature. Okay. So at room temperature, what essentially happens is that you always have thermal generation and recombination of electrons and hole pairs, right? You cannot do anything. It's a thermal phenomenon. It's going to happen. So now at all point of time, everywhere in the piece of silicon, mobile electrons and mobile holes are getting generated. Not only there, here also, mobile electrons and mobile holes pairs are getting generated. Now, can you comment on what's going to happen to the mobile electron hole pairs which are just at the surface? Okay. So regardless of what type of impurity you have doped your silicon with, you are always going to have thermally generated electron and hole pairs all the time. Their concentration might not be big enough, right, large enough, but you are always going to have mobile electrons and holes. So that's going to happen at the surface also all the time. This phenomena we have neglected so far, but now since that surface is devoid of almost every mobile charges, that phenomena cannot be neglected right now.
When I have counter to this, say like we have high positive charge there. So even if electron hole pair is increased, why won't the electrons go down?
It will. That's the next thing, right? The electrons are going to go down, but the holes are going to stay. Right? So that's the exact thing I wanted to make that point, and thankfully he made that point. So you are going to have this electron and hole pairs which are going to get generated, but the electrons are going to get pushed out and the holes will remain. But the good thing is that these holes are all mobile. They are positive mobile charges, right? So after you apply some critical electric field, right? What is the critical? That's a different thing, but looks like there is a way of applying some critical electric field where I can fill that part just underneath with positive mobile charges. Now, if I apply a battery between the both sides, right, here and here, I am going to get the movement of charges, right? And that movement of charges is only going to happen underneath. It's not going to happen through the bulk because the bulk is always reverse biased. Make sense? Okay, so we'll discuss that in a slightly more amount of detail in the next class. But I hope I have been able to give you an idea of how you can electronically control the mobility of carriers, right? So this is not possible in case of a metal. This is only possible in case of a semiconductor, because you have this interplay between mobile charges and immobile charges, and you can play almost God, right? To figure out, okay, I want holes to contribute, I want electron to contribute. Okay, okay, thank you.